Today I'd like to look at a line integral through this vector field we see here. And so just in case, what that vector field is doing is to every point in the 2D plane, it's assigning the vector x squared, y squared. And when we compute our line integrals, we typically write them this way, f dot dr. To be practical about it, this is usually what we do to compute them. We find some function r of t, which represents the curve we're traveling along, and we sub that into our vector function up here above, and then we proceed with a dot product with the derivative of r prime of t and go from there. So that's what I want to do. And then at the end of this problem, when we're done finishing the value of it, we're going to consider another way to do it, something else for you to look for that will possibly simplify your calculation in very special circumstances. So let's take a look. First off, we want to parameterize this parabola here. So we're saying that the curve we're moving along is the arc of this parabola, y equals 2x squared from this point to this point. So whenever you have y equals, it's easy to parameterize. You just say x of t is equal to t, and then you write y of t equals, and you write the same function again, but instead of writing, oops, we don't need to write y again there, sorry. You just write that 2x squared, but you write 2t squared instead. And you can see by substitution that if x were plugged in for t, we went right here, you'd have this same function up here. And then what you want to do is also make sure you restrict t so that you stay between the two given points. You want to stay between the point -1, 2 and the point 2, 8. So just make t start at -1 and end at 2, and you'll do it. So this thing here is your parameterized parabola between the given points, and we sometimes call this r of t. So now we're ready to compute this line integral. Let's not forget the vector function we're using is x squared plus y squared, well, x squared I plus y squared j. Okay, so let's do that. So f of x comma y equals x squared I plus y squared j, and we know that r of t is equal to the function x equals t, y equals 2t squared, with the domain from -1 to 2. All right, here we go. Integral of f of r of t dot r prime of t dt. So here we are. Integral f of r of t is going to be t squared I plus 2t squared j. Now, if there's any doubts what that's coming from, what we're doing is we're taking these two things and we're subbing them in here wherever it says x and y. So that's what we did. If you realize this is where x used to be, and this is where y used to be, in this expression up here. Okay, and then we're going to do the dot product with r prime of t. So we take the derivative of this thing. So the derivative of x equals t is just 1 times I, plus the derivative of 2t squared is 4t and j. And then this is going to have a dt at the end, and we're going to go from -1 to 2. Okay, so moving ahead, this is just be careful with your dot products. So what dot products tell you to do is multiply the x components together, and then afterwards multiply the y components together and add them. So we multiply those exponents together, we have 1 times t squared, which is just t squared. Then we're going to say plus, and then this expression, 2t squared squared, is really 4t to the 4th, but then it's getting multiplied by another 4t, so we get 16t to the 5th. And then we have dt integral -1 to 2. Right, so this is a pretty simple integral, right? We do our antiderivatives here. What do we get? We get 1/3 t to the 3rd plus 16, oops, I wrote 15 there, sorry. 16 over 6 t to the 6th, evaluated from -1 to 2. So we're going to plug that 2 in first. You know, 1/3 times 2 cubed plus 16 sixths times 2 to the 6th minus whatever we get when we plug in -1. Now that's sort of just bashing through some arithmetic, so I'm going to let you do that. Why don't you pause the video for a minute and calculate it and see what. So I ended up getting 171. Okay, so that's it. That's the value of the line integral. It's positive. This means the vector field helped us a little bit along the way. Now, it turns out this vector field is special because you can express it in another way. We can say that this vector field is the gradient of some scalar function f. So our vector field here equals gradient of some scalar function f, where that scalar function would be the following. 1/3 x to the third plus 1/3 y to the third. Okay, so how do I know that? Well, I know what a gradient vector is. A gradient vector is the vector of partial derivatives. So you take the partial derivative of f with respect to x and the partial derivative of f with respect to y, right? And then what you do is you check it. So what I sort of did here is I actually did an antiderivative in my head. I knew something whose derivative would be x squared would be 1/3 x cubed, and I knew something whose derivative would be y squared would be 1/3 y cubed. And so that's what I was really doing here. Okay, so I can check this if I want. If I take this is my scalar function. If I take the derivative of this with respect to x, like I would do that first part, this becomes x squared. And the derivative of 1/3 y cubed with respect to x is just 0. So it ends up having the correct first element. And then if I want to go for partial f, partial y, well, the derivative of 1/3 x cubed with respect to y is 0, so that's gone. And the derivative of 1/3 y cubed with respect to y is y squared. So there's the second part of my vector, and sure enough, this vector is really the original vector field. So it turns out that if a vector field f of x comma y is equal to the gradient of some scalar function, then the vector field f of x y is, you could say this two ways. We can say conservative, or maybe a more intuitive title for this would be path independent. And what that means is that independent of path, you would get the same value for your line integral. So in our case, we did the line integral of this function, f of r of t dot r prime of t dt, and we had used a parabola that went from the point, in case we forgot, here it is, -1, 2 to 2, 8. So -1, 2 to 2, 8. Well, since this vector field that we're dealing with, f of x comma y is equal to x squared I plus y squared j, since it's equal to the gradient of f, where f is equal to 1/3 x cubed plus 1/3 y cubed, then it's a path independent vector field. So it doesn't matter how you get from this first point to this second point, the same amount of work is going to be done. And so what you can do in this case is speed things up quite a bit. What you do is you take these two endpoints that you have and you evaluate that scalar function. So f of x comma y, right, is 1/3 x cubed plus 1/3 y cubed. And so what I'm going to do now is I'm going to find f of 2 comma 8, and I'm also going to find f of -1 comma 2, and I'm just going to subtract them. So in other words, if I just subtract the value of that scalar function somehow, these two scalar function evaluated these 2 points, I get the total amount of work that's going to be done to me. You could think of this like a potential. So what do we have? 1/3 of 2 cubed plus 1/3 of 8 cubed. So I can tell you if you do that, let's see, 8 cubed plus 2 cubed and then divided by 3, right? Because really they're both being multiplied by 1/3. We end up getting 520 over 3. Here, if we do 1/3 of -1 cubed plus 1/3 of 2 cubed, then we end up getting, let's see, we have -1/3, right? Plus 8/3. We end up getting 7/3. And then if we just subtract these two things, because this is, we ended here, we started here, we subtract to find the difference in these things. If we do 520 minus 7, and then we divide by 3, we end up getting 171. So that's sort of the fast way to do these line integrals. You can find this function, which is sometimes called the scalar function, or the potential, and you can then just evaluate your expression, your new scalar function here, whatever this thing is, at the two endpoints and get a result. Okay, so the only trouble happens sometimes is that it can be challenging for someone to think about a function that would have the derivative that you want it to have. So for example, let's take a look at one and try and figure out what the scalar function. Okay, so let's pretend we have something even more complicated. Let's pretend we had a function of a vector function of 3 variables, and this is what it looks like: y squared I plus 2xy plus e to the 3z times j plus 3y e to the 3z k. All right, and what we want to do is we want to find a function. Let's just do it. Let's write it this way. So we want to find f of x comma y comma z such that the gradient of f is equal to capital F, our vector function up here. Okay, so just remember what a gradient is. It's the vector of partial derivatives. So this gradient vector is going to be partial f partial x, partial f partial y, and then partial f partial z. Okay, so let's do this one at a time. If we're going to have a scalar function that's going to work, then it would have to have y squared as a partial derivative with respect to x. So it must have a term that looks like this, xy squared, because that's the only thing that when you take the derivative of it with respect to x, you get y squared as a result, which needs to happen for it to be the gradient vector. Okay, let's look at the next term. So now this needs to be the derivative with respect to y. And interestingly enough, if you look at this term, the derivative of that term I just underlined in green with respect to y is the 2xy, which you see here. So we don't need to worry about that. But we need to get this thing, the derivative of something with respect to y has to be e to the 3z. So we must have a plus y e to the 3z, because that would give us the correct derivative for this term. Because if we took the derivative of this with respect to y, we would get this e to the 3z. And then lastly, if we look at this last term here, we need to have this be the derivative with respect to z. But sure enough, if you take the derivative of this term here, I'm underlining at the bottom with respect to z, the y is just a constant sort of hanging out there, and the derivative of e to the 3z is e to the 3z times 3. If you multiply by the derivative of the exponent, but that's the term, that's exactly the term you have up here. So this thing here is the scalar function for that has a gradient of this vector field. So what does that mean? That means that this vector field is conservative or it's path independent. So finding the line integral between any 2 points just means you plug the 2 points in and subtract those values. So that's actually a pretty cool thing. All right, so I think I'm going to stop there. I want to say thanks for watching.